In this video, we're going to look at Newman projections. Newman projections are a way of drawing a molecule where you're looking directly down the bond that connects two atoms. It is a useful tool when considering different conformations of the same molecule. The conformations of a molecule refer to any of the infinite number of possible spatial arrangements of atoms within a molecule. Specifically, these spatial arrangements come from the rotation around single bonds, and it involves a single molecule, not breaking bonds and talking about different molecules. The number of conformations is infinite, and each of the conformations are called conformers. The term that comes from the combination of conformational isomer. Newman projections allow us to look at specific conformers of a molecule and compare them with one another. There are infinite numbers of these, but we typically look at the highest and lowest energy conformers of a particular molecule. Now we'll look at a simple example. Consider the molecule ethane. Ethane consists of two carbon molecules that are connected together with a single bond and is fully saturated with hydrogens. If we draw ethane in 3 dimensions, it will look something like this. Remember that the wedges indicate that those hydrogens are pointing out towards us, and the dashes indicate that those hydrogens are pointing away from us, while the lines indicate that those bonds are in the plane of the drawing. If you're having trouble seeing how this indicates ethane in 3 dimensions, make a model of this molecule and make sure that you can understand where each bond is in your 3-dimensional molecule on the 2-dimensional drawing. A Newman projection allows us to look at the different conformations of a molecule like ethane. For a Newman projection, we have to look down the carbon-carbon single bond for which we are drawing conformers. In this case, I'm going to look from left to right, from carbon 1 to carbon 2. If you have a model of this molecule, it can be helpful to look at the model in the way that I've drawn on the paper. When we look in this direction, carbon 1 will be in front and carbon 2 will be in the back. The way that we draw that with a Newman projection is by making carbon 1 a point in the middle and by making carbon 2 larger in back of or behind carbon 1. Because in ethane, all of the substituents on the Newman projection will be the same, they're all hydrogen, I'm going to letter the hydrogen so that we can follow them from the 3-dimensional drawing to the Newman projection. Now we're going to place hydrogens A through F onto the Newman projection in the conformation drawn in our 3-dimensional structure on the left. If we're looking from carbon 1 to carbon 2 in this direction that is drawn here, hydrogen C will be pointing down and towards us on carbon 1. The way that we indicate this on our Newman projection is by drawing it straight down like this. Hydrogens HA and HB will each be pointing respectively up and to the right or up and to the left. Remembering, of course, that we're looking down the carbon 1 to carbon 2 bond in that direction. In the conformation I've drawn on the left in our 3-dimensional structure, on the back carbon, carbon 2, hydrogen D is pointing straight up, essentially between hydrogens A and B. Hydrogen E is pointing down and to the left, and hydrogen F is pointing down and to the right. If you're having trouble seeing this, what I would recommend is to make a model of ethane with each of the hydrogens a different color. Then turn that model so that you're looking down the carbon 1 to carbon 2 bond so that you understand how the Newman projection corresponds to the 3-dimensional conformation of ethane. This Newman projection shows ethane in a single conformation, or conformer, where all of the hydrogens are as far apart as they possibly can be. We can describe the extent of rotation around the carbon-carbon bond using something called the dihedral angle. The dihedral angle is the angle between one bond on the front carbon and one on the back carbon. and is represented by theta. The dihedral angle in this particular conformer is as large as it can possibly be for ethane, 60 degrees. In a molecule where all of the dihedral angles are as large as possible, in other words, 60 degrees, this conformer is given the name staggered because all of the bonds appear to be staggered relative to each other. This is the lowest energy conformer of ethane that we can draw. Remember that each of these bonds from carbon to hydrogen contain electrons. Therefore, they have a negative charge and they repel one another. That's why this is the lowest energy conformer of ethane. Now let's consider another conformer, the highest energy conformer of ethane. Unlike the staggered lowest energy conformation of ethane, the highest energy conformation will have all of the bonds overlapped with one another, pushing those negatively charged electrons as close together as possible. This will look like a Newman projection like this. For this Newman projection, I have taken the front carbon and held it steady while rotating the back carbon. The back carbon has rotated by 60 degrees, causing all of the carbon-hydrogen bonds to be overlapped. Of course, we can't draw them that way, so we show them slightly staggered from one another, but this is called the eclipsed conformation because the front carbon-hydrogen bonds are eclipsing or blocking the back ones. Here, the dihedral angle is said to be 0 degrees. In an actual molecule of ethane at room temperature, the carbon atoms are rotating with respect to each other constantly, millions of rotations per second. And there are an infinite number of conformations because the dihedral angle can be anywhere from 0 to 360. While there is enough energy at room temperature for ethane to rotate continuously, there is a slight increase in energy needed for it to be eclipsed versus staggered. The difference in energies between the staggered and eclipsed conformers is about 3 kilocalories per mole. In other words, the eclipsed conformer is 3 kilocalories per mole higher in energy than is the staggered. We can show this difference graphically. We can compare the staggered and eclipsed energies by graphing the potential energy versus the dihedral angle, as shown. The difference in energy between staggered and eclipsed, as already mentioned, is 3 kilocalories per mole. That means that the eclipsed conformer is 3 kilocalories per mole higher in energy than is the staggered. At a 0 degree dihedral angle, we are at 3 kilocalories per mole, and at 60 degree dihedral angle, we're at 0. Keep in mind that the potential energy axis is relative, not absolute. As we go from the staggered to the eclipsed conformation, the energy rises rapidly as it reaches the eclipsed conformation. This increase in energy as we move towards a dihedral angle of 0 shows as resistance to rotation. This is called torsional strain. The energy required to overcome torsional strain is called torsional energy. As mentioned earlier, at room temperature, the molecule has access to plenty of energy that allows it to overcome the torsional strain and therefore can rotate rapidly, giving an infinite number of conformers. We can use Newman projections to consider the conformers of even more complicated molecules than ethane, which can give us a lot of information about the three-dimensional shapes of these molecules.